Hello friends, myself Professor T.S. Vandali. Today I am going to explain about heat transfer through one-dimensional composite materials. So before you go through the heat transfer, that is comes under fourth module, that is axisymmetric problems and the torsion of shaft and conduction of heat through composite wall. So in this chapter, some of the important problems that is related to purely conduction and convection. So I am going to explain few problems. First of all, we come to know what is conduction. Conduction is the transfer of heat through materials without any net motion of mass of the material. This is represented by the equation Q is equal to minus QA into dt by dx. Q is nothing but the heat transfer rate in x direction in watt. K is the thermal conductivity in watt per meter Kelvin, a property of the material. Already we discussed in the first chapter, that is the displacements, or we are going to find out the stiffness of the stepped bar. E is the property of the material, that is Young's modulus. But in case of heat transfer, Q is the property of the material, K is the property of the material, that is watt per meter Kelvin, and dt over dx is the temperature gradient in Kelvin per meter or degree centigrade per meter or centimeter. Similarly, convection, the definition of convection is the heat transfer process in which the thermal energy is transferred between solid and a fluid surroundings. That is, the rate equation is given by Q is equal to HA into T minus T infinity, where Q is the convective heat transfer rate in watt, H is the convective heat transfer coefficient in watt per meter square Kelvin, T is the temperature of the surface of the body in degree Kelvin, and T infinity is the temperature of the surrounding medium. These two properties of the materials, that is conduction and convection, we are going to solve some of the problems. Sometimes left side conduction, right side convection is there. Sometimes left side convection, right side conduction is there. Just I am going to explain this problem, that is very important for the exam point of view. Just concentrate and how to solve, how to obtain the intermediate temperatures. But in case of stepped bar, we are going to determine the displacements, that is q1, q2, q3, so on, and stresses developed and global stiffness matrix. But in case of temperature, the thermal conductivity of the materials, we are going to find out the intermediate temperatures. So for that, just you go through this problem. What is given in the problem? First we are going to concentrate the problems, that is an induction furnace wall is made up of three layers, inside, middle and outer layer, with thermal conductivity K1, K2 and K3 respectively, as shown in figure. Determine the nodal temperatures, means we are going to find out the intermediate temperatures. The given problem is made up of three materials, that is inside, middle and outside, three composite wall. At left side there will be a conduction, and left and right side there is a convection. Each composite wall lengths are given 25 centimeter, 5 centimeter and 3 centimeter, and thermal conductivity, that is material property, is given in the problem. It is K1 is 8.5 watt per meter Kelvin, K2 is the property of the middle composite wall, 0.25 watt per meter Kelvin, K3 is 0.08 watt per meter Kelvin, H is the heat transfer coefficient, 45 watt per meter square Kelvin, and T infinity is the 30 degree centigrade is the surrounding temperature. First, the given units are in centimeter. We are going to consider that centimeter to meter, because the temperature, that is thermal conductivity K1, K2, K3 are given in watt per meter Kelvin. So the given lengths we are going to consider in meter itself. So for that length L1 becomes 25 centimeter, becomes the reduced, considered in meter, that is 25 centimeter. L2 is 5 centimeter, L3 is 3 centimeter. Okay, so the temperature, the units are in degree Kelvin. So how to convert that given temperatures, that is centigrade to degree Kelvin? Already we are knowing 273 is added to given temperatures. So T1 is given 6 left side conduction, that is 600 degree centigrade. We are going to add 273. The total temperature we are obtained is T1 is equal to 873 degree Kelvin, and T infinity at the right side there will be a convection, that 273 plus 30, it becomes 303 degree Kelvin. H is the heat transfer coefficient. Similarly, bar elements, we are going to draw the FE model. So consider the linear diagram as shown in figure, that 1, 2, 3 and 4 are the nodal, are the nodes, and T1 is the temperature in the first element, T2 is the temperature in the middle element, and T4 is the temperature in the in the third composite material. But inlet and outlet temperatures are given. We are going to find out the temperature that is at intermediate T2 and T3, that we are going to find out. So in this also it is very simple. The thermal conductivity matrix in case of bar element K is equal to A, that is AE upon L into 1 minus 1 minus 1 1. But in case of thermal conductivity, the stiffness matrix is given by, that is for pure conduction, Kc, C means pure conduction, Kc is equal to Ak over Le into 1 minus 1 minus 1 1, where A is the cross sectional area. We are going to consider as unique. Suppose area is not given, we are going to consider unique. K is the thermal property of the material. It is given that for the first element K is equal to K1, and Le is the equivalent length of the composite wall. It is given L1 is equal to 25 centimeter. So these values we are going to take it considered in the above equation, that is Kc means thermal conductivity of the first element becomes, that is A is equal to 1, that is unique. K is 8.5 divided by 0.25, that is 25 centimeter is considered in meter, it becomes 0.25. 1 minus 1 minus 1 1, that matrix is, we are going to get the elements as shown in below, 34 minus 34, 34 and 34. Similarly for the second element K2 is equal to, that is A2 K2 by L2 into that stiffness matrix minus 1 1 minus 1 1 minus 1 minus 1 minus 1 1. At that time the elements becomes 5 minus 5 minus 5 and 5. Similarly for the third stiffness matrix K3 is equal to, we are getting 2.6666 minus 2.666 minus 2.666 minus plus 2.666. So the global stiffness matrix can be obtained by Kc is equal to K1 plus K2 plus K3. Okay, so global stiffness matrix is reduced to, you are getting the size of the matrix is 4 by 4, because the 4 nodes are there, 1 2, the 3 composite wall means having 4 nodes. The size of the matrix is becomes 4 by 4. Okay, now where the right side there will be a heat generation, heat, that is convection, since at node 4 heat is lost to the surrounding by convection, because it is exposed, that is stiffness matrix due to convection is given by, for convection, k kc kh, h indicates the convection matrix. Okay, see kh at end conduction means to the surrounding, that is ha into 0 0 0 1 is the standard formula it is for the convection matrix. Just you have to substitute the values, that is kh end is equal to, that h is the heat transfer coefficient, h is given 45 and cross sectional area is unique, that's 0 0 0 1 are the matrix. You simplified, you are getting 0 0 0 4 5, 45 is the matrix. Then we are going to write the size of the matrix for left side conduction is 4 by 4. Now this at the right end convection is there, you have to consider that matrix into 4 by 4. The element is same 45, the size of the matrix becomes 4 by 4, it becomes 4 by 4. Now the global stiffness matrix can be written by the k is equal to left side conduction and right side convection. You have to add both the matrix by addition. You are getting the matrix as, the final matrix as 34 minus 34 0 0 minus 34 39 minus 5 0 0 minus 5 7.666 minus 2.666 0 0 minus 2.666 47.66. This is the equivalent stiffness matrix, thermal conductivity matrix. Okay, now like similarly for the bar elements, we are going to write the free end convection. We are going to write the force vector, that can be written by fh end is equal to ah t infinity in the vector 0 1. A is the cross sectional area, h is the heat transfer coefficient, t infinity is the surrounding temperature. So just we have to substitute, we are getting the force vector, that is for fh end is equal to, the element becomes 0, the force vector becomes 0, 13,635. Now global force vector F is equal to, size of the matrix is 4 by 4, the only one column, the elements are 4 elements. Now equilibrium equation is given by kt is equal to F. Already we are knowing in the, we are going to solve the problems on stepped bar, so that is kq is equal to F. Here it is kt is equal to F, you have to write. Then the second row of the global stiffness matrix we have to consider, that is second row in the global stiffness matrix, that is minus 34 39 minus 5 0 t2 is equal to, so then second row, just you substitute, multiply that second row with the column minus 34 into t1, 39 t2 minus 5 t2 is equal to 0. So already we are knowing the temperature t1, so t1 is equal to 873 Kelvin. So 39 t2 minus 5 t 5 t3 is equal to 29,682. Okay, thus eliminating row and column corresponding to, that is t1, replacing that second row with equation with equation, we get that size of the matrix is 3 by 3, 39 elements are 39. You have to delete the first row and first column, because at left side there will be a conduction, so you have to, that is you consider as the fixed end, so in as in case of stepped bars. So you are getting the size of the matrix 3 by 3. On simplification we get the nodal temperatures, t2 is equal to 846.25 Kelvin and t3 is equal to 664.35 Kelvin and T4 is equal to 323.21 Kelvin. These are the temperatures we are going to obtain by simplifying the matrix by considering the stiffness matrix for pure conduction and for convection. Just go through it, you can understand. Okay, if you are having doubts, please call me later. I will call back and clarify your doubts. Thank you, one and all.